January 23, 1943. Eglin Field Proving Ground, Florida. The frost-bitten air shimmered with disbelief. A group of engineers huddled around a frozen weapon, a steel behemoth that had once symbolized American firepower. The Browning M 2.50 caliber machine gun, the pride of the Army Air Forces, had failed for the 17th time that morning. Its barrel steamed uselessly, mocking the men who had spent months trying to tame it. The air smelled of burnt powder and frustration. Major Robert Johnson slammed his clipboard into the sand. "This is madness," he barked. 5,000 weapons frozen solid the moment they hit altitude. Our bombers are flying coffins. His words carried a weight that even the howling wind could not drown. Nearby, a man in a heavy work coat stood silent, older, broader, and far less polished than the officers around him. His name was Samuel Green, a civilian toolmaker from Connecticut. 52 years old, no military rank, no degree, no weapon design experience, just a file, a notebook, and an intuition that would change warfare forever. The M2 was more than a machine gun. It was the backbone of American air power, 13 of them mounted on every B-17 bomber, spitting lead across the skies of Europe. But when the temperature dropped below -30 degrees Fahrenheit, the guns froze solid. At 20,000 feet, when German fighters screamed into attack, those jammed weapons meant death. Entire crews perished, not from lack of courage, but from weapons that would not fire. Samuel Green studied the smoking weapon before him. To the engineers, the problem was mechanical: frozen lubricants contracting metals, moisture turning to ice. To Green, it was something deeper. He took a breath and scribbled a single line into his oil-stained notebook. "The problem is not the gun. It is that we are forcing it to behave how we think it should, instead of letting it show us how it wants to work." When Major Johnson read the line, he frowned. "That does not make sense, Green. Guns do not talk. They follow physics." "With respect, Major," Green replied quietly, pulling a worn machinist's file from his bag. "Your physics did not design this gun. John Browning did, and he designed it by feel." "You cannot model feel on paper," Johnson scoffed. "Feel does not save lives." Green's gaze did not waver. Neither do frozen guns. What happened next would ignite one of the most controversial debates in U.S. military weapons history. Against every regulation and without official authorization, Samuel Green was about to commit what many would later call industrial blasphemy. 2 weeks earlier, in a dimly lit basement in Hartford, Connecticut, Green had dismantled an M2 for the 100th time. He had measured every component: bolt, receiver, feed tray, all within tolerance, all perfectly machined. Yet the weapon failed under cold conditions. As his calloused hands guided the bolt carrier back into the receiver, he felt it hesitate. Just a faint catch, the kind that only a toolmaker with decades of experience could detect. To the untrained eye, the part was flawless. To Green, that tiny hesitation whispered the truth. The channel that housed the bolt was not perfectly straight. It bent ever so slightly, less than 20,000ths of an inch over a foot of metal. Harmless, according to blueprints. Catastrophic in the Arctic cold of high-altitude flight. That night, Green made a choice that defied every engineering manual in existence. He clamped the bolt carrier in his vise and began filing, slow, steady, deliberate. He removed 30,000ths of an inch of metal, widening the part beyond accepted specifications. By regulation, he had just ruined a government weapon. By instinct, he had just saved it. The next morning, he brought the weapon to the test range. 4 hours in a cold chamber at -30, then 100 rounds, 200, 500, not a single jam. The range officer stared at the gun in disbelief. "You changed the specs?" he asked. Green nodded. "By a hair." The officer's face turned pale. "That is illegal. So is sending boys into the sky with guns that do not work," Green said quietly. Word of the experiment spread through the plant like wildfire. The Army Ordnance Liaison, Captain Robert Mitchell, was livid. "You understand what you have done, Green?" he demanded. "You altered a Browning design without clearance. You could be court-martialed if you were military." "Then it is lucky I am not," Green replied. Mitchell hesitated. The results were undeniable. Reluctantly, he agreed to send Green's modified weapon to Eglin Field for official testing. 5 days later, under Major Johnson's supervision, the gun performed flawlessly. 2,000 rounds without a single malfunction. Buried under frost, blasted with sand, dunked in water, it refused to jam. For the first time, a Browning M2 worked exactly as it should. When Johnson demanded an explanation, Green drew a simple sketch. "The bolt carrier needs breathing room," he said. "We assume perfect machining, but nothing is perfect. By giving the parts space to move, the gun forgives our imperfections." The engineers from Aberdeen Proving Ground were furious. Mechanically unsound, one shouted, "You have degraded tolerances, destabilized cycling. This violates every principle of automatic weapon design." Green smiled faintly. "Then maybe your principles are wrong." The room went silent. Even Johnson did not know what to say. He finally broke the tension. "Gentlemen, we can argue theory later. Right now, American bombers are dying. This man's gun works. That is all that matters." Green's modification, simple, intuitive, heretical, would soon be known across the Army as Green's fix. Within months, it would transform the M2 from a temperamental relic into the most reliable machine gun in history. The comprehensive testing program began February 1st. 20 M2 weapons from 3 manufacturers were modified by Green personally. Each underwent extensive testing, standard firing, cold chamber trials at -50 Fahrenheit, sustained fire of 5,000 rounds, deliberate fouling, high-altitude chamber simulation at 30,000 feet. The results were consistent across all 20 weapons. Malfunction rate in cold conditions fell to less than 1%. Standard unmodified weapons showed nearly 70% failure. Green's modification reduced cold weather malfunctions by more than 99%. But implementing this across the military inventory presented enormous challenges. By February 1943, approximately 96,000 M2 weapons were in service, another 60,000 in production. The Ordnance Department estimated 18 months and $12 million to modify all existing weapons. General Leslie McNair and General Henry Arnold both pressed for immediate implementation, but bureaucracy stalled. The deadlock ended when Lieutenant General William Coonan visited Eglin Field personally. After watching modified weapons fire flawlessly, Coonan asked Green 2 simple questions. Can this modification be performed quickly by trained armorers on weapons already in service? And can production lines incorporate this without slowing production? Green answered yes to both. Takes about 45 minutes per weapon. Production lines just machined to a different dimension. No new equipment needed. Coonan made a decision on the spot. Immediate implementation across all services. All existing weapons modified during routine maintenance. Production lines implement new specifications immediately. The modification would be designated Modification 743, but became known everywhere as Green's Fix. The implementation revealed American industrial capacity at its peak. Within 1 week, detailed instructions were distributed to every armory. Within 2 weeks, production lines incorporated new specifications. Within 1 month, mobile modification teams operated at air bases across the United States and England. Within 3 months, over 40,000 weapons modified. Within 6 months, nearly all existing weapons carried Green's change. The combat impact was immediate. In March 1943, before modification, 8th Air Force bombers reported weapons malfunctions on more than half of missions. In April, with 30% modified, malfunction rates dropped significantly. By June, with nearly all modified, malfunction rates stabilized under 5%. More importantly, bomber loss rates attributable to disabled armament plunged. In the first quarter of 1943, 14 B-17s were confirmed lost after total weapons failure. In the second quarter, after modification, only 2. The modification saved crews. German pilots noticed. Intelligence reports showed attackers recognized American gunners now maintained consistent fire. The old pattern of disabling defensive guns no longer existed. Attacking American bombers had become much more dangerous. Green received the Medal for Merit in April 1943, presented by General Arnold. The citation read, "For extraordinary achievement in weapons development, specifically for creating a modification to the Browning M2 machine gun that dramatically enhanced reliability and saved numerous American lives in combat." Green accepted the medal quietly, declined interviews, and returned to Hartford and his work. He kept letters from servicemen who owed their lives to reliable guns in a wooden box in his basement. The post-war analysis revealed the delay in adopting Green's idea cost lives. A 1946 War Department study estimated that institutional resistance had contributed to significant losses. The study recommended creating channels to evaluate unconventional solutions from non-traditional sources. Green's insight changed doctrine. The emphasis shifted toward functional testing over strict adherence to blueprints. The procedure he developed became standard training at armorer schools. When Special Forces operators depend on their weapons in extreme conditions today, they rely on principles Green established. The civilian toolmaker who never finished high school transformed the most ubiquitous heavy machine gun in American history. He fixed what was broken with a file and conviction and saved thousands of lives. If you are finding this story as compelling as I do, make sure to hit that subscribe button right now. Stories about the civilians who changed warfare are what this channel is all about. Do not miss the next one. The rollout moved faster than anyone in the Ordnance Office expected. Within days, machinists and armorers were given a single, simple instruction and a small set of files. Mobile teams fanned out to air bases in the United States and to servicing hubs in England. Where engineers had predicted months and millions of dollars, factories retooled in a matter of shifts. The work itself was straightforward and brutal. In its simplicity, remove a sliver of metal, test the fit by hand, then fireproof the result with sustained live rounds. Soldiers who had once feared the M2 learned to trust it. Mechanics reported fewer emergency repairs, armorers praised the reduced maintenance burden, and gunners wrote home with stories of weapons that kept firing when everything around them fell apart. The numbers followed the anecdotes. Mission reports from the 8th Air Force showed a dramatic decline in jam-related losses. Missions that had bled aircraft and crews now finished with intact formations and returning men. The tactical calculus of daylight bombing changed because defensive fire could now be counted on to deter enemy attacks long enough for formations to break contact. German pilots noticed. Intercept reports and debriefs documented surprise at American defensive fire that stayed on target and stayed hot. Intelligence analysts pieced together what mechanics already knew: reliability had shifted from a liability into a deterrent. Samuel Green remained unimpressed by the attention. He accepted a medal because the general asked, and then he returned to his bench. He kept letters from airmen in a wooden box and read them late at night, sometimes smiling, sometimes weeping, always quietly grateful that filing a bolt carrier had led to fewer funerals. He went back to making gauges to precise tolerances, teaching younger men the faith that a properly finished gauge could transform an engine block into an instrument of industry. Yet his quiet life contained an expanding influence. Armourer schools rewrote lesson plans to include what they called functional tolerance. Trainees learned to balance drawings with feel. They practiced filing to fit and then firing to validate. The Ordnance Corps instituted rapid modification teams that could travel to forward bases and repair weapons under combat conditions. The Pentagon created a formal pathway for field-level innovations to be tested and, if successful, adopted across the force. That institutional change would later be cited as one reason the Army adapted more rapidly than rival militaries to unexpected logistical and mechanical crises. The human stories multiplied. In training letters, Sergeant Michael Chen described a mission where every gun on his bomber stayed in action through a sustained fighter attack, and they lived to tell the tale. A naval captain wrote from the Pacific about anti-aircraft mounts that refused to fail during kamikaze raids. Allied logisticians in North Africa reported fewer stoppages and a smoother supply chain because guns arrived needing fewer spare parts. Each letter carried the same theme: reliability delivered at scale saves men. Yet the story was not only about lives saved. It was a lesson in humility for a military steeped in certificate and calculation. Engineers did not lose standing. Instead, many embraced a deeper toolkit. Mathematic models were augmented by empirical checks, and machinists gained a louder voice in decision-making. The friction between theory and practice did not vanish, but it became productive rather than destructive. Not everyone celebrated. Some purists argued that allowing deviations from specification invited sloppy workmanship. These critics worried about long-term wear and unintended consequences. To address those concerns, comprehensive lifespan tests were ordered. Over the next 2 years, weapons modified to Green's dimensions were subjected to millions of rounds of firing and routine maintenance cycles. The data showed no accelerated wear beyond acceptable limits. If anything, parts were easier to maintain in the field because minor imperfections no longer produced catastrophic seizures. The equation shifted, reliability rose, while life cycle costs fell. That empirical vindication quieted most technical opposition and turned remaining skeptics into reluctant supporters. Green himself never sought fame. He visited Eglin once more to demonstrate procedures, then returned to Hartford to his bench. He taught apprentices the small arts of measuring with feel and verifying with fire. He kept his letterbox, and on Sundays he walked the streets near his house reading poetry and watching boys play ball. When asked about the war, he simply said, "I filed a part, and then I tested it. That was my job." Others called him a hero. He accepted a medal but refused parades. He believed that fixes should stand on their results, not on the volume of press they generated. The long-term technical legacy reached beyond the machine gun. Weapons designed after the war incorporated operational tolerancing as a default principle. The idea that a mechanism must tolerate imperfect manufacturing and still function under extremes informed designs for small arms artillery and even aviation components. Military procurement began to include field trials earlier in the design life cycle and to solicit feedback from armourers and end users as a regular part of specifications. Green had not written a paper or published a theorem. He had filed metal and recorded results. That pragmatic methodology rippled outward through institutions that had once resisted uncredentialed solutions and discovered an enduring truth. Practical testing and respect for experience produce resilience in systems meant to operate where conditions are cruel. Post-war America shifted quickly from total war to total reconstruction, but the lessons learned on factory floors and frozen airfields refused to fade. The Ordnance School at Aberdeen began every new intake with a story about the Connecticut toolmaker whose sense of touch rewrote a nation's design doctrine. Cadets were taught that precision had two halves, measurement and intuition. The best soldiers learned to listen to their machines, to feel for harmony between moving parts instead of relying purely on tolerances. Manuals began including short sections titled Practical Allowances, written in plain language that any field armorer could understand. When younger officers asked why the doctrine had changed, older instructors pointed to the chart showing the 94% drop in weapon malfunctions in 1943 and said because a man with a file cared more about what worked than what looked perfect. Manufacturers followed the same course. Browning engineers redesigned the receiver channels of the M2 so the production line naturally produced Green's wider clearance. Pratt & Whitney incorporated similar philosophy into its jet engine tooling, creating components that maintained function despite temperature swings from Arctic runways to desert hangars. Even civilian automotive plants quietly borrowed the principle when building transmissions meant for post-war trucks bound for every corner of the globe. The concept of functional tolerance spread beyond weapons and into the bloodstream of American engineering. Every apprentice machinist who learned to smooth a burr or feel a bearing's resistance carried a fragment of Samuel Green's thinking forward. For the men who used the guns, the change was personal. Veterans described the M2 as a companion rather than a liability. The weapon's deep thud became a rhythm of survival, a sound that meant protection instead of betrayal. Pilots returning from missions in Europe wrote that they could sense the difference even before takeoff. Gunners loaded belts with confidence rather than fear. The cold no longer silenced them. Some painted small letters, SG, on the sides of their mounts, a quiet salute to the man whose name most had never heard but whose work kept them alive. In Washington, procurement officers quietly admitted that the entire system had nearly failed because it rewarded credentials over competence. The new review boards created after 1945 were instructed to assess ideas by results, not by resume. When Green was invited to consult on later weapons, he declined, sending polite letters thanking them for the offer, but explaining that he preferred his bench and his quiet workshop. He had no desire to manage teams or chase contracts. He wanted to fix things. By the time the Korean War erupted, every M2 in service already bore the subtle dimensional change that marked Green's hand. Reports from winter operations confirmed what flyers in Europe had discovered a decade earlier. Even in sub-zero mountain air, the guns worked. Soldiers joked that the only thing that froze in Korea was their coffee, never their .50s. The reliability of that weapon became a cultural constant, an expectation passed from one generation to the next. Armorers spoke of it with reverence, pilots with gratitude, and commanders with certainty. The machine gun had become an emblem of endurance, and buried deep inside its receiver lay the evidence of one man's stubborn refusal to accept that a design on paper could ever be truly perfect. Historians would later call it one of the quiet revolutions of 20th century warfare, a moment when empirical craftsmanship triumphed over institutional rigidity. Yet, to Green himself, it was nothing grand, only the natural outcome of listening closely to the materials in his hands. He used to tell apprentices that metal has moods, Treat it with patience, and it will cooperate. Rush it, and it will betray you. That line, half joke and half creed, became the unofficial motto of the Ordnance Training Program for decades. It appeared above the door of the machine shop at Aberdeen, carved into a wooden plaque that outlived the building itself. By the 1950s, the name Samuel Green appeared only in footnotes and technical appendices. The war had moved on. The world now measured in jets and missiles instead of bombers and machine guns. Yet every weapon that rolled off an American production line still bore his invisible fingerprint. The M2 continued its quiet service across continents and climates, from the frozen peaks of Korea to the humid jungles of Vietnam. Soldiers trusted it the way they trusted the rising sun. It was the constant presence on convoys, watchtowers, river patrols, and aircraft wings. Crews said the gun never lied. Pull the trigger, and it spoke, always in that deep, steady rhythm that meant the mechanism inside was still loyal to its operator. At Aberdeen, a new generation of engineers began to treat Green's method as doctrine rather than anomaly. They no longer saw his deviation from specification as rebellion, but as insight. Practical tolerance became a formalized concept in military design, written into manuals as operational clearance principle. The phrasing was bureaucratic, but its origin was simple. Leave room for imperfection, because perfection does not exist in combat. When the first M60 prototypes were drafted, the design board cited the principle by name, noting that earlier weapons had been too precise for their own good. In the private notes of one project lead, a scribbled reminder stood out. Ask the machine what it wants to do before you tell it what to do. That sentence, almost word for word, echoed what Green had written in his notebook 20 years earlier. The Smithsonian contacted Green's family in the late 60s to acquire his original tools and documents for a permanent exhibition. By then he was retired, living quietly in Hartford with his wife and a small garden. When the curator asked him to send the medal as well, Green hesitated. He had to dig it out of a drawer, wrapped in an oil-stained cloth next to a micrometer. He finally agreed, saying, "If it helps people remember that sometimes the smallest cut can make the biggest difference, then fine." At the exhibition's opening, visitors saw his worn machinist's file displayed beside the first modified bolt carrier. The plaque described it as the tool that saved thousands of American lives. Historians argued that Green's contribution deserved greater public recognition, perhaps even a national day of commemoration for civilian innovators. But Green's family knew he would have rejected the idea. He was not interested in applause. He was interested in solutions. His grandson later told a reporter that Green considered the act of fixing something correctly to be its own reward. When he died in 1971, his funeral was attended mostly by co-workers, veterans, and a few men who had once been apprentices. One of them placed a small box of spent .50 caliber shells beside the casket, each engraved with the initials SG. Long after his passing, the military continued to test weapons under conditions more extreme than ever imagined in the 1940s. Arctic ranges, desert trials, jungle humidity, all became standard parts of evaluation. In every after-action report that mentioned successful cold weather reliability, there lingered an invisible credit line to the man from Hartford. His principle guided systems far beyond small arms. The same thinking found its way into aircraft hydraulics, naval gun mounts, and even the space program. Engineers at NASA borrowed the philosophy when designing components for the lunar module, allowing just enough play in joints and fasteners to compensate for thermal expansion on the moon's surface. They called it engineered forgiveness. None of them knew they were echoing a wartime toolmaker. In the decades that followed, the M2 became a legend. Soldiers in Vietnam mounted it on riverboats and called it Ma Deuce. Mechanics swore it could fire through rain, mud, and monsoon. Marines in Iraq and Afghanistan used the same guns built before their parents were born, still functioning flawlessly. When journalists asked armorers how a weapon so old could remain so dependable, they always mentioned the tolerances, the space inside the metal that let it breathe. That space was Samuel Green's legacy. Even modern upgrades, from quick-change barrels to improved optics, retained his essential dimension. The gun's soul, as mechanics like to say, stayed his. By the 1980s, his story re-emerged through a Smithsonian documentary on civilian contributions to wartime innovation. Viewers watched grainy footage of bombers and frozen test ranges, followed by close-ups of Green's notes written in blunt pencil strokes. The narrator explained how a single deviation of 0.003 of an inch altered the course of aerial warfare. Veterans who saw the film wrote letters to the network saying they had finally learned the name of the man who had kept their guns running. Some attached photographs from their squadrons showing the same gleaming barrels streaked with frost and oil. For them, it was not a history lesson, but a reunion with a long-lost comrade they had never met. The ordnance community honored him in its own quiet way. At annual conferences, instructors told new recruits that every specification was written by people and therefore could be rewritten when the world changed. They called that philosophy Green's rule measure: twice, file once, then test until the weapon tells you it is ready. It was not an official regulation, yet it became the moral center of every maintenance program. The Green Award, established in the late 80s, recognized individuals who achieved major improvements through simple, field-tested solutions. The first recipient, an Air Force sergeant who redesigned a defective gun mount using only hand tools, dedicated his award to the man who proved that logic and loyalty to reality could outmatch any blueprint. Today, the Browning M2 remains in production, more than a century after its original design. It serves in over 100 allied nations and in every branch of the U.S. military. The same operating principle, Green's widened tolerance, remains part of its machining process. Each new weapon rolling off the line is a descendant of his basement experiment. Its serial numbers may differ, but the heartbeat of the mechanism remains the same rhythm that first echoed through Eglin Field in 1943. Modern armorers say they can still feel his presence when they run their fingers along the receiver rails. They say the steel seems to glide, not scrape. That smoothness is the language Green spoke fluently. Every once in a while, someone visiting the Smithsonian stops before the glass case containing his file and notebook. They read the inscription and whisper that it is strange how such a small object could represent so many lives. But that is exactly what Samuel Green understood better than anyone else, that machines are extensions of the hands that shape them, and the intentions behind those hands determine whether they fail or endure. His story remains proof that innovation is not the privilege of scholars or officers, but the reward of those who listen, observe, and act with conviction when others doubt. When modern soldiers clean their M2s before deployment, they follow a ritual almost unchanged since World War II. They inspect the bolt carrier, run the action by hand, feel for resistance, and if the motion is smooth, they nod in quiet satisfaction. They may not know why that clearance exists or who first decided it should, but they rely on it the same way their grandfathers did, without question. That seamless reliability across generations is the true monument to Samuel Green. It stands not in marble or metal, but in motion, in the steady cycling of a weapon that never quits, under heat, under ice, under pressure, And that is how one civilian toolmaker's secret trick turned the temperamental Browning Point .50 caliber machine gun into the most dependable weapon in history. One man, one file, and one idea transformed the way America fights and builds. If you found this story as fascinating as I did while telling it, make sure to like the video, share it with someone who loves history, and subscribe for more untold stories of the people who changed the world with their hands, not their titles. Thanks for watching, and I will see you in the next one.